So hello, welcome, ladies and gentlemen. My name is John Pitelud. I work for the World Wind Energy Association. I'm coordinating the small wind section of the association, and it's my pleasure to moderate the first panel or the first session of small wind during this conference. As a reminder, after this session, we will have in the same room another session on small wind. We have in this session a lot of presentations. It seems to be very packed. So I will not take too much time on presenting each speaker, so we have enough time at the end for questions or after the presentation. So I will just start right away with the session. So I will now present or introduce Eugenie Kryshkova from the Universidad Autónoma de Chipango from Mexico, the Chapingo, sorry. He will talk about some new measures to new device to measure the torque of small wind turbines. So, floor is yours, Evgeny. You have to again share your screen the same way you did it last time. So you have to share content.
Okay, thank you very much. 1 second. Oh, it is now.
Yes, it is. If you can put it on presentation mode or full screen, that would be nice. Yes,
Okay, it is.
yes, it is perfect. Go ahead.
Okay, good day or good evening. I don't know. I'm staying in Noche in Mexico. My name is Romanchika Eugenia Krichkova, Eugenie. I'm working in Chapingo Autonomous University in Mexico. And department mechanical agriculture mechanical engineering, yes, and post graduation in agricultural engineering and integral use water, yes. It is my email in Mexico. Thank you very much for invitation in this World Wind Energy Conference Congress, World Congress. Yeah, I'm present about a new method and device and measuring the torque of small wind turbine. Yes. Uh, First, I working about my university, my department. We have one center, Renewable Energy and Biosystem Center. In this, yes, we have different systems, photovoltaic, digester, wind energy, and solar dryers. It is for my this uh, academic investigation, research, and other person. It is a solar thermal system, different solar thermal systems, and parabolic, etc. Yes. And wind energy systems. Different wind systems we development uh, design new wind turbines, yes, and construction and evaluation. And greenhouse, we have extractors and greenhouse dryers, and the determination, efficiency, and effectiveness. Different parameters we measurement and analysis. Uh-huh. It is solar dryers, photovoltaic, we have solar photovoltaic and wind energy for dryers. Greenhouse solar dryers with solar thermal and photovoltaic system and wind energy. And these solar dryers and other, excuse me, these solar dryers is photovoltaic for dryers and another, and greenhouse the other one. Yes. different products dryers in this drying in this installation, no? So tomate, potato, banana, etc. We determination cost energy for these dryers in order. So in the West, in agricultural greenhouse are used to develop different plants. Yes, this is different greenhouse. In this greenhouse installation, extractors for renewable the air and lower the temperature. About these instructors, systems, energy photovoltaic systems, etc. By what so many extractors are installed to keep the climate in optimal condition. Yes, to improve the performance of the extractors of the outlet cones and place it. Yes, are placed where it is more important. In the extractors, the electrical energy is transformed into wind energy and is lost in the atmosphere. Extractors, electrical energy is transformed into wind energy with very, very big velocity and is lost atmosphere. Yes. And we think what by installing a wind turbine in front of the extractors, and wind turbine installed from the extractor, we verify that a good part of the electric energy can be recovered from the residual air. 50%. 50% it is possible to recover the air residual. Okay. It's extractor with cone, wind turbine. It is my patent, Mexican patent, installation in greenhouse wind turbine for production electricity, or we have one pump, hydraulic pump, and installed in this turbine. In case of the design or evaluation of the wind turbine, the energy analysis are current output in the wind energy before passing through the blades. The mechanical energy and the electrical energy finally generated by the wind turbine, yes? For this measure of the operation parameters are carried out with the help of different sensors. Pressure, velocity, force, in order to determine the mechanical energy, aeolic energy, wind energy, electric energy. It is necessary to measure a torque development by the blades. Or mechanical engineer is a torque and revolution. Yes, and we wow. Excuse me. Yes. We one thing. Don't know why. It is change. No. Change. Yes. With development cone, extract, and wind turbines together in one device. It is designed. And with construction, it is construction the cone, the wind, turbines, and structures. Yes. Okay, with development and installing and test this device, but it is one time is this to change. To improve the terms of work, is necessary to carry out the different improvement test and evaluation. Yes. The new uses of small vent turbine, the new uses of small turbine, or the new methods and device for their testing and evaluation. Yes. It is new band testing. According to the patent, other patent, Mexico patent, 2020, a test bed was developed for wind turbine installed. Wind turbine installed from a structure. This structure used in greenhouse and to recover the energy. With cone, with one cone, with two cone, with three cone, different cone. And in different points we measured different parameters. Yes. Extract test bench together with wind turbines. It is a scheme construction. Okay. But it's very difficult to measurement torque by what we have different sensor, torque sensor, ring torque, rotative torques, yes, but existing torque sensor are installed in the rotating shaft with causes changes and modification in wind turbine design. It is a small wind turbine. It is very difficult. It's very difficult to change modification in design. Yes, it is different sensors, torque sensor. We have in other installation. My department is agricultural and mechanical, and we working with tractor and other machine. We use this torque sensor. But in wind turbine, small wind turbine, it is very difficult to use this torque sensor. Yes. And we have another method of measuring torque is bireaction. The reaction torque is the torque required to be applied to the stator of rotation device so that it does not rotate with the rotor. It is a scheme, torque measurement by reaction. It's different. It's different. In this method we use forces sensor. It is a scheme force and length is a torque. I don't know. And bireaction, other method to measure the torque, bireaction. It is a scheme. I don't know why it is. Yes. And it is a scheme to application. It is static torque measurement. Static, yes? A static torque measurement. What others? Perfect. Excuse me. One moment, and to use my present device for measuring torque, a low power wind turbine. Yes, it is. It is a scheme. It is a model method of the installing, yes, no. Installing is, yes. Is development this device. This device, where is installing wind turbine? Yes, in this base. And with wind turbine in this base, we have axis or axis, excuse me, axis, other, yes, axis, and bearing, 5 bearing, 4 sensor, 7, 4 sensor, 4 sensor. But instrumentation with Arduinos and PS. In this equation, torque is force for length. Force, this force and length. It is very, very simple, but it's very difficult to think about this device. It is a scheme, yes? And we, construction, design and construction this device to measure the torque of a small wind turbine, different in this base, in this base. 1 second, I have to computer in different. My is the change in conference. It is, but so it is the construction, design, the device, the test, small wind turbine, installing. Yes, installing in this axis, and reaction torque is in this force sensor. Force sensor. Wow. No, it is. It is small and base in installation. With this device, we measure on torque and calculation the energy, mechanical energy, and balance energy, mechanical, electrical, and wind energy. Okay. So, in the conclusion, in fin, we receive a different measurement torque in different condition. One moment, we have where other presentation, other. One moment. It's, it is, oh no, different. Installation, device from after an instructor left, after instructor, and after wind turbine. 2 wind turbine, and you measurement torque in this and in this. It's very interesting what direction, velocity, R velocity is different. No, is what? It is the result, any result to torque measurement in calculation the power, mechanical powers of after an instructor and after a wind turbine. Yes, I don't know. Very interesting for examination, analysis, balance of energy. Yes, in other, excuse me, very. One moment is for change this. I don't know.
Sorry, again, you have 2 minutes more.
Yes, 1 minute, 1 second to change. Ah, yes. No, it is all. Yeah, it's finished. It is a test result, a small wind turbine with a torque sensor. It is torque. It is torque and it is in time, different condition. Thank you very much.
Thank you, Guinea. Very interesting presentation. It's good to hear that in Mexico there's some research and development on small wind, because so far small wind has not played a role in Latin America, but we see a lot of potential. So there are some questions in the chat. I also have questions for you, but I will leave it until the end so we have time for the other speakers. So if you can wait until the end of the session for questions. So thank you very much for the presentation. So our next speaker, I believe he couldn't make it today, is Soren Jensen. If you are there, Soren, please just raise the hand. Otherwise, I will go ahead with the next speaker, which is Ravindranath from the company Unitron. So I will go ahead with you, Ravindranath. Please, floor is yours.
Thank you so much. Thank you so much. So should I share my screen then? Yeah. Can you see my screen?
Not yet.
Not yet. PowerPoint. Okay. Can see now?
Yeah, if you can go to presentation mode or full screen, will be.
Yes, presentation mode. I'll go.
Okay.
Yes.
Yes, perfect. Thank you.
I want to thank WWEA, especially Jami Hussain and his team for giving me this opportunity. I don't want to, go into it. Let us proceed with my presentation straight away. This is Unitron at a glance. We have a worldwide presence and empaneled, as you see, MNR in India, Serim Malaysia, AEC Australia, LECO in Sri Lanka, and two of the models are qualify ISO 61400-2 by CVET, now DVET. And we have conventional model as well as new 3D models, which we were using it for. And in fact, what something like Eugene has displayed, we are also working on waste wind, what is coined, I would like to put it as waste wind energy converter, you can call it. So that is the main focus of this turbine, but it is suitable for open wind applications also. We are been identified by NIDEC Japan for manufacturing alternators for their turbine. And these are our brief manufacturing facilities. As everybody knows, aware, there's no supply chain for small wind. So we have to be independent, self-sufficient. Even magnets are produced in-house. We have a capacitive discharge magnetizer. We produce magnets in-house. Everything we have to be self-sufficient for small turbines. Unlike large turbines, there is somebody giving gearbox, somebody giving alternator. That may not work for small turbines in general. This is our close-up view. This is the this is the overview of summary of small wind energy at a glance. This could be updated, I think, recently. This is wind energy potential, as you see, and 3% fact is actually it is 3% of the solar. It's a very interesting fact to know that 3% of the solar energy is coming from converted as wind energy, and 3% of the global potential is enough to meet the demand, global demand today. And World Bank survey says it's only about 15 to 20% is land mass is suitable for large scale extraction of or megawatt scale turbines. about 20 to 25% of the world landscape is no good for any kind of energy, but a whopping 60 to 65% has potential for small scale wind energy, provided you have a capability to extract energy from low wind speed regime, like say 3.5, 4, effectively you have to come into that sub 5 levels, 0.5 meter per second, what I mean. Now, this is what is the turbine which we are working on. I'm already produced a few turbines and we have put in the toolings in place, which actually the conventional kinematic equation will not apply for this turbine. It's actually sweeping volume. And when I look at the turbine, people think it is a drag machine. No. And the pressure is created on the hind side of the blade, not in the front of the blade, hind side. This is the basics of the technology. You can see both the surfaces of the blades are active. Wind stream hitting on the concave surface leaves a right angle at almost with the same speed. And then it creates a high pressure and creates a lift on the back side of that blade. So it's a push-pull action, which actually working. So which means you exceed the Brett's criteria to a large extent, because it's not actually Brett's criteria do not apply for this kind of what you call extraction technique. That may be okay for conventional wind turbine using aerofoil rotors. So this is the blade which we have produced using vacuum thermoforming. Engineering plastics like ABS, polycarbonates can be easily produced with thermoforming, and the process also will ensure perfect geometry and repeatability, since it is produced by, produced on the die and vacuum. Advantage of this is a low RPM, extremely low noise, less than 25 dB, work best for rooftops, and turbine spacing can be as close as their 3D spacing, 2D spacing do not apply here again. You can put as low as 1 diameter or 1.5 diameter without, worry about wake effects. Okay. This is what I'm telling, industrial waste. See, most of the industrial ducts are 0.5 meter to 1 meter, but at a very high speed. Wind turbines will be 30, 40 meter per second. Maybe sometimes 15, 20 meter per second. But conventional turbine, first thing they create, now even Eugene has displayed a turbine, but third, I'm sure that is a conventional turbine from AirX or I think Southwest Wind Power. Such turbines will create a back pressure on the prime mover. That means ultimately installing such turbines will put additional load on the blower motor. This is practically zero static. There is no back pressure when you install this turbine for such applications. So you can see, even if it is assuming 300 days of working, you can annual savings will be about $1,700 and cost of installation is about $5,500. This is just a ballpark figure. This is actually practically we tested in one of the cement factories. You can see such a small duct when the wind turbine is installed here. And we have clocked as about 5.5 to 9 meter per second. Even for such low winds, we have clocked 600 watts, 5 to 600 watts. By putting a conventional turbine, we could clock only about 70 to 80 watts. This is because of this 3D rotor aerodynamic, we could achieve this. And when the VFD was at full speed, we achieved 1.5 kilowatt. So 1.5 kilowatt is very attractive to put back into the grid, like I've shown. No need to store energy in batteries or anything like that. Directly online transfer into the grid. And sometimes we have also, what we have tried is very small ducts. We have tried to modify the tip of the duct by installing a cone, so that what happens is the wind will get diverted. Doesn't matter even if the wind speed is reduced a little bit, but it will cover entire rotor diameter is within the wind spread region. So this is, we are trying at Ultratech Cement very soon by modifying their duct for better energy attraction. This being very small turbine in high power, now what Eugene has showed, it's about, I think, 1.2 meter and must be about 400 watt. With 1.8 meter, this turbine produces 3 kilowatt. Now you can install about every electrical substation, majority of the electrical substation, the substation load, that SCADA itself is about 150 kilowatt. So now some transmission companies are planning to install small turbines near the substation. That means there will be about 20-30 towers. Each tower will accommodate about 4 to 8 turbines, like I've shown here. So which means you can extract as much as 30 kilowatt on each tower. Similarly, you can install these turbines on telecom towers too. You can say you can create a cross arm and put, since if it is a conventional turbine, the cross arm length would be too large. This is a high power and low diameter being only 1.8 meter or even 2 meter extension or 3 meter extension cross arm can easily take the load of telecom tower. So you can extract the energy like this. You can install these on boats because it's a very small diameter and there is no back pressure or no static. It won't create any this load on the prime prime moving. Boat. And this can be used now for electrical. We are working with eCharge Bay in India, who are creating electrical vehicle charging stations on the highways. So you can have, since turbines can be spaced closely with solar and hybrid, almost 1 megawatt could be generated on the electrical highway. I mean for EV charging stations. Like this, you can install even on the rooftops. On compact spaces, you can have turbines next to each other. My own house is powered by a 7.5 kilowatt hybrid. And recently, about 3 weeks back, I bought an electrical vehicle and I made sure that my EV is charged by wind solar hybrid system. So far, I did about 400 kilometers in less than 3 weeks without drawing a single unit from grid. So it has been an EV working on renewable energy is more greener than when you use grid for charging the battery, I feel so. So use of renewable energy of any form and capacity will make even 100 watts is cleaning up of 10 tons. Governments and Terry, and I'm sure they will give us a lead to take a big leap forward in this direction. Thank you.
Thank you, Ravindranath. Very nice presentation and very nice technology. You're probably one of the few small wind manufacturers in India. So it's very nice that you are continuing with the research and development of new products. So I have several questions for you, but I will again leave it till the end, so we have enough time for everybody. So I will go ahead with the next presentation. The next presenter is Edwin Newman, who will talk about how to improve efficiency of a different kind of wind turbine, a typical horizontal, but a new type of turbine. So Edwin, floor is yours.
Yeah, can you hear me?
Yes, we can hear you now.
Okay. I don't have any pictures on this end, so I'm going to have to describe what the invention is. This is an explanation of my US patent 11125-207. And it describes a straight-bladed Savonius rotor, but this has many other applications, which I hope I'll have time to get into. Now, on each curved surface of a Savonius rotor, there's a vertical center line, if you can imagine that. And on either side of this vertical center line is what you might call a Magnus rotor. It's a long, thin tube which is run by a motor. And it has suitable air guides. Now, each rotor is set spinning in the opposite direction away from the center line. And if the angular velocity is greater than the wind, then this action creates a volume of low pressure of air ahead of the blade, drawing each blade forward. So, but it's not the Magnus effect that is at work here, but the Coanda effect. Now, this new structure acts as a propeller, but instead of the swept area being circular, it's rectangular and fits the shape of the underlying vehicle. Let's see. Now, the Magnus force itself has been used to create lift and has been studied both theoretically and experimentally in equivalent conditions of airspeed, projected area, and air density. And a Magnus rotor, which this may be called, will produce about 10 times the lift of an airfoil if the Magnus rotor is spun fast enough. The formula for the power to drive a roller is the power equals the coefficient of friction times the density of air times the cube of the angular velocity figured in rads per second times pi times the radius of the roller to the fourth power times the length. Now, in calculation, the power needed will be found to be very low. And this formula is used to calculate windage losses in driving any shaft. Now, this invention can be made to fit a contoured underlying shape, not just the Savonius rotor. The method for that is in U.S. patents 3120275 and 1586750. Now, I said that these rotors can supply 10 times the lift of an airfoil, and for that I'm referring you to the United States Department of Energy grant report. It's called DOE/R6/0969. And that would be on page 2, and there's many references that are given at the end of the report. So the principle of this invention can also be applied to the front of a ship, which can be made bluff-bodied, as they say. And let's see, an aircraft wing, and an automobile, a blimp, and wind energy turbines, both of the vertical and horizontal type. So if an aircraft wing is to be swept back, then I would recommend the roller to be in the shape of an Archimedes screw. That should take a little more power, but not very much. You're talking about the very, very low power to run these rollers. So that's all I have to say. I hope you can get it without pictures.
Thank you, Edwin. Yeah, it wasn't easy to imagine everything without the pictures, but yeah, I think we got the idea. I have a few questions also, but I will leave it until the end. Just maybe if you can, if it's possible, that you can give your email address in case somebody has questions. Or maybe at the end I will ask you again. And
Well, I can give you the email address now. Actually, I sent email to your office, but I guess it got mixed up.
okay, no problem. So then we
well,
have it. So if any, yeah.
Well, I'll give you an email address now. That's enewman2010@hotmail.com.
Perfect. Good. And if anybody has questions about the email later, you can send an email to organizer of the conference, and we will give it. So maybe some people will have questions, but if any other question, I will leave until the end. So please stay with us in this session, and I will come back to you at the end. So I will go ahead now with the next presenter, which is Mr. Suresh. I see you are here. Please go ahead. Yes, thank you.
Screen. Hope you're able to see it.
We see the screen. If you can go to presentation mode.
Yep, 1 minute.
Yeah.
Yes.
Perfect.
So great. So first of all, thank you for giving me an opportunity to speak here. And me and my colleagues from WRI India, we worked on estimating the small wind turbine potential in Tamil Nadu, which is a state in India, using geospatial data. So this also forms a methodology for estimating the small wind turbine potential. So I'll just start with what the definition of a small turbine. So probably since we are all in like a small wind turbine panel here, this is probably not required. But for the sake of completion, I'll just go through it. So the small wind turbine based on the IEC definition is defined based on the rotor swept area. So whatever is when the rotor swept area is less than or equal to 200 square meters, this can be called a small wind turbine, and when it operates in the voltages of around 1000 volt AC or 1500 volt DC. So the swept area of 200 square meters approximately corresponds to a rated power of about 50 kilowatt. And for our convenience, we can informally further subcategorize it based on the rated power into mini, micro, and pico based on the rated powers. So this slide might be of more use because here we can see that up to about 50 kilowatt is what is the IEC defines as a small wind turbine. And if we explore the previous schemes by MNRE, we can see that they have referenced up till 100 kilowatt. And if we check the list of large wind turbines, the RLMM, the list of manufacturers for large wind turbines and the approved models, we can see that the large wind turbines are starting somewhere around 225 kilowatt. So this area between here needs a bit more of clarity as to which category probably it falls under. And moving on. So also just looking through the NIWE empaneled and certified wind turbines and models in India. So there are about 7 manufacturers, suppliers. Mr. Ravindranath from Unitron can probably correct me if I'm wrong. And there are about 13 turbine models that are certified based on the previous empanel list by NIWE. So moving on to the context of this research work. So we know that the state of Tamil Nadu has very high wind potential, and it is one state in the country with the largest installed capacity of large utility scale wind. So this installed capacity is about 9.6 gigawatt. So compared to this, when we see the numbers for the small wind turbines in Tamil Nadu, the numbers are not, they have not found such an uptake. So the installed capacity of small wind turbines based on the 2018-19 MNRE annual report data, it's not more than 257 kilowatt for Tamil Nadu. This is when looking at both small wind turbines operating alone and small wind turbines installed as hybrid systems when combined with solar and different RE options. So combined, the installed capacity is not more than 250 kilowatt. So currently, the ones that are functional and considering only small wind turbines, the capacity will be much less. So, and also why go for small wind turbines? Also, Mr. Ravindranath from Unitron pointed out a lot of reasons. But small wind turbines, they are easier to install, operate, and can be deployed at locations unsuitable for large wind turbines. So as he had mentioned in the presentation, about 60 to percent of the landmass, I mean, of the windy areas can be used by installing small wind turbines. So, and they are also a decentralized RE option, and DREG options are becoming popular. And they can be close to, installed close to locations where there is a need for energy. And they can be considered in the mix. So hence, a study that maps out the locations in Tamil Nadu where small wind turbines, I mean, are suitable for small wind turbine operation. And if we can estimate the approximate potential, that would be a way forward. So hence this was carried out. So the methodology followed for the same is first we looked at the average wind speed. So this is not like a micro level study where we need site specific data. We looked at it from more of a macro level where the whole state was considered. So when looking through the specifications of the certified wind turbines in India, and then going through the data and also through stakeholder discussions, it was, it came out that about 4 meters per second and above. So if a location has about an average wind speed of about 4 meters per second above, it can be considered suitable for small wind turbine installation from a wind resource standpoint on a macro level. And second, we further filter this. So considering all the windy areas, a lot of them have installations of large wind farms. So the best windy sites have already been, large wind farms and wind turbines exist there. So we checked for locations like are there locations that have good wind speeds, but there are no large wind farms or large wind turbines to extract energy from the wind. So these locations, so probably although these locations are not, they don't contain large wind turbines due to constraints stemming from infrastructure or transportation, but may be suitable for the installation of small wind turbines. Second, the wind resource along the coastline. So Tamil Nadu is blessed with a large coastline, and of that we found that about 13 districts, the coastline, and about 7 of the 13 districts are suitable for small wind turbine installation from a wind resource point of view. And also we combined the wind resource data with demand locations. Like for example, small wind turbines are typically used in agro applications, in farms, grinding, generating electricity, rural and urban areas, powering industrial applications, etc. So such clusters and such use cases were also mapped out in the state and combined with the wind resource data to check for potential areas that where small wind turbines can be deployed. And also the existing technology, that means the approved list of small wind turbines, have also been investigated to come up with the study. So looking at the wind resource and considering wind resource of about 4 meters per second above at a hub height of 20 meters, because 15 to 20 meters are typical for the operation of small wind turbines, we find that about 18% of the state is suitable for small wind turbine installations from an average wind standpoint. And looking into this a bit deeper and mapping out the wind resource based on the average wind speed, the darker the color, the more the wind resource, we can see that there are about 21 districts in Tamil Nadu where small wind turbines can be considered for installation based on the average wind speeds. And ranking the districts based on the intensity of the wind speed in those districts, we can see that no surprises there. Coimbatore, Theni, Tirunelveli, Tenkasi, where the large wind farms are there, come under number 1. Kanyakumari, Tirupur, Madurai, certain districts are there. And also rest of about 15 districts are there where small wind turbines can be considered from a wind resource standpoint. So looking at locations where there is a good wind resource, but do not have large wind farms or large wind tapping activity. So we see the map on the left, the red dots are large wind farm clusters, and rest all the turbines are locations where there are large wind turbines or a large wind turbine installed and large wind turbine farms and clusters. So from this, we can see that about 7 districts are there where there is a good wind resource in Tamil Nadu, but there is no large scale extraction of wind. So small wind turbines may be explored in these places. So like, for example, just taking the few examples like the Nilgiris, they are mostly hilly areas. So installations of large wind might be difficult, but small for habitations and for powering different applications there, small wind turbines may be suitable. Same for districts like Krishnagiri, etc., where there is a sufficient wind resource for small wind turbine application, but have not yet been tapped for large wind. Now exploring the coastline, so there are about 13 districts that span the coastline of Tamil Nadu, and about 7 districts providing a coastline of about 835 kilometers is suitable from a wind resource standpoint for the installation of small wind turbines. And we have also estimated the potential. So from the coastal districts, so considering like a standard wind turbine from our list of empaneled turbines, from the list of empaneled turbines by NIWE, and based on certain approximations, we can estimate the approximate potential to be around 720 megawatt. So this is just an approximate figure of what is possible if small wind turbines are tapped along the coastline in Tamil Nadu. So once more, next we have explored different energy demand centers. Like we know that small wind turbines are used for different applications like agro, farming, industrial use, for battery charging, for urban rural homes, for powering them, etc. So such use cases are mapped out and conclusions drawn in this figure. So in the figure on the left, we can see that all these use cases are mapped out. So the darker greens are the ones where there is more of agro and farming activities carried out. The green dots are industrial, micro, small and medium and MSME clusters, and the blue being major cities. So looking at all of this data in totality, we are able to draw some conclusions that the districts of Tirupur, Coimbatore, Tirunelveli, Krishnagiri, they demonstrate an overlap of good wind potential and multiple demand areas. And when considering coastal districts, the districts of Tuticorin and Nagapattinam, they also exhibit a good potential because they combine multiple use cases. I mean, they are proximal to multiple use cases with a good wind resource. So the map on the left is a site suitability study based on different constraints keyed into the GIS software. So the dark greens are the areas where it's suitable for small wind turbine installation based on the constraints that have been inputted. And overall, we find that based on the estimations for these particular use cases, there is a potential of about 4 gigawatt that is currently an untapped potential of 4 gigawatt approximately in Tamil Nadu based on the criteria that is considered. But however, listening to the presentation today and considering Mr. Ravindranath's new wind turbine design which can be placed much closer, and it's not dependent on the old micro siting guidelines, etc. Probably when considering machines like that and when exploring options, such low wind speed options, the potential might be much more. So I would like to conclude by that, and this was a joint work by myself and my colleagues Akanksha and Kajol at WRI India. So thank you. And any questions?
Yeah, thank you, Mr. Suresh. Very interesting research, and I think it's extremely important, this research, to develop some kind of market for small wind in India. This is what we need. We just need to complement it with something else, but we can talk about after this, at the end of the session. So thank you very much. And again, I will have some questions, but at the end of the next presentation.
Sure.
So thank you very much. So our next presenter is Chenupati, and excuse me, my Indian colleagues, if I don't pronounce your name very well, from Sunflower. I think I see you there, so floor is yours. Thank you very much.
Yeah, thank you. Thank you for this great opportunity to present Sunflower Propeller here.
Thank you very much.
Yeah, what you see here is a sun. Basically, it's a propeller which looks like a sun. Actually, basically it's a micro wind turbine. My name is Siva Chenupati. I'm based in Munich, Germany. I'm working on this propeller. It's new technology. I'm the inventor of this propeller. I'm working on this for more than 3 years now, full time. Good. That's how it rotates, and it looks like a sun, but in reality, it's a propeller, and the blades are in the shape of rays of the sun. and the center hub is the sun, which is much smaller than the blades. So it's a pretty unique design. That's why it got the name sunflower for the actually. So the problem we are tackling or trying to solve is this is a high value problem. Everyone knows it. There's a lot of pollution caused by mobile phone towers in India. It's about like 4.5 lakh, 450,000 masts are running on diesel generator in India. Actually, this is really expensive because they have to fill like these 1,000-liter tanks every month. It's too expensive, like cost like around 7,000, 5,000 euros, 7,500 euros per year, and not only expensive, it's very polluting. It accounts for about 2% of India's CO2 emissions. This is the thing which we are is a big problem. People think my data is almost free, like I pay only 200 per month, but in reality, it's very dirty business. That's what's going on right now. So the solution is already kind of existing. You can put a small micro wind turbine next to a mobile phone tower. Technically, it works. There are some fundamental issues. Problems is the mast is very expensive. You have to put a separate mast because the wasted drag force on the mast, like it creates a huge torque on the tip of the tower, and that one needs a very solid foundation and extra mass. And on top of that, the standard screw propeller turbines need more than 3 meters per second, and most of the time they are sitting idle. So in places where you have only less than 3 meters per second, it's of no use actually. Most of the time they might be sitting idle. So this is a very expensive solution, and most of the time it's sitting idle. So our idea is to move that thing to put it on top of the tower without needing any extra supports or hanging supports. You can directly put it on the top and get higher wind speeds because on the top you have very high wind speed. So this is the whole idea. This is the high value solution we are talking about. You get more power because you have more wind speed, and because any wind is coming in, it doesn't push the it doesn't create the drag force on the tower. This propeller uses both lift and drag forces to create the power. So this is the big advantage of this propeller. And so you don't need an extra crane to put it on the sides. Usually end up having a crane if you want to install something, standard screw propellers or standard wind turbines on the side of the towers. So you can't reach them because you need a clearance to the tower. So these problems can be solved. So we have kind of pretty new technology, and we have 3 working prototypes. And one of the biggest advantages, the one which you're seeing there is directly mounted on top of the car. You don't need any mast because the blades are not coming down and cutting whatever thing there. So you need a minimum mast required is some small clearance and the radius of the micro wind turbine. So standard ones. But this one being rotating in the shape of a cone, a vertical cone, you don't need any clearance to the ground or any mass for the clearance of the ground. And PCT is already filed. We have this published in February 2020. And we showed this. What you see in my background is the same one. We showed this in Abu Dhabi in World Energy Council in 2019, actually. So that was the first model. And right now we have almost final close product. And we are doing the field testing right now for 1 to 2 kilowatt version, which is going on right now. So if you see the history, actually, what you see on the right side is a 5,000-year-old version wind turbine. What you see on the extreme right is the top view of this turbine. It's a paddle wheel. Technically, it will work. You can put it in the water or in the wind, but the only thing is you have to make sure is you have to submerge the water only 50%. The other part of the wheel should be in the air. Actually, same is the case if you want to use it as a wind turbine. You have to build a wall around it, so that only 50% of the wheel is exposed. So this is well-known technology, and it's been, even today, these things are working. Yeah, this is nothing new. So about 100 years ago, like a German scientist, professor in Seattle, actually, from Patrick Christian, actually, he developed a mechanical drive chain to rotate and revolve these blades synchronously, so that he made it so that you can eliminate the wall actually. It works pretty good, but it's not scalable. So we are, after 100 years, we are the first one to make this hub compact and make this everything in a small size hub, because we have to put all those things into the radius point where the radius is 0, because it's at the tip of the cone, which is inverted cone actually. So by doing that, the whole thing becomes scalable and easy to do it. So the whole idea is like the Christian Boeing propeller is what you see on the left side, which has a huge hub where you have all the mechanism to control it, and we made this small actually. And what you see here on the bottom left is from 1920 from Boeing Historical Museums. It's a huge hub, and this is being made for and used for in 1920 for making boat propeller. In 2017, German University of Siegen, they tried to reduce the size and they made it. It's also like it's a cylindrical form, and we are the first ones to make this in a small size and compact, and we were able to put all that mechanism into a small hub, and it's possible. And many people think that it's not impossible, but we made it actually. Everything into that small section to rotate and revolve the blades synchronously. So we have done the simulations just for testing and simulating. We just started with a small blade, 1.5 meter blade with a core angle of 45 degrees. Using AirShaper CFD simulations, the simulations came out to be around 45% efficient. And so right now we are doing more advanced simulations. And we came out that the optimal tip speed ratio around 0.8 gives the highest power. We will use our MPPT controller to run at that maximum power peak point. So this is all feasible. And simulations the simulations what we did are very similar to the University of Siegen, which they did in 2017 in Germany. So there's not much of a difference if you put the blades in a cylindrical form or if you put the blades in a cone form. It looks like it's very similar results we're getting. And right now we are optimizing the blades shape using neural networks, which is going on right now in Switzerland by Aero GmbH. They are supporting us to do this simulation. Good. So the market size is pretty big, and half of the population has no access to internet connection. It's not because of they cannot access mobile phones. It's because of the expensive towers which are running with diesel generators. This is a big problem in India and Africa also. We have a huge potential also in many islands in Philippines and South America. There are many mobile phone towers that are running on diesel generators. It's a global problem, not just India or Africa, South America. There are many places where this can be implemented. The global TAM is quite big actually. It's close to 1 million units. So this is the first kind of testing we're doing on a car. Actually, just it's easy to test it. So we have both, so wind direction sensor and wind speed sensor. By using that, we can change the angle of the blades. The yaw mechanism gets very simple because you don't need to change the whole wind turbine to the direction. If in case we have high wind speeds, we can also change the blades and make it. We can stop it so that it doesn't rotate, and blurring is also gets pretty simplified and pretty easy actually. So yeah, right now we are looking for support to scale it and start production in India actually. Also looking for support. As I said, the TAM is quite big. So the current target is to reach 100,000 units per year. So yeah, these are the current applications, but technically this propeller can also be used in other applications for tidal energy. And we can also use this propeller. We have measured it already. It generates pretty good amount of thrust if you are using it as a propeller for drones. At very low RPM, we can also use this at very low. It doesn't generate so much of noise. We can use this for generating thrust for drones also, which is still undergoing and plan to make. We also have some interested customers for making this kind of underwater drones for doing oceanography and sensing if there is any minerals or oil and gas exploration. So we have customers who are interested in doing it. Basically, it's kind of a fish which will swim like a fish, and there's a low risk of any nets or any grass winding up to a standard screw propeller. So more user friendly. It doesn't cut any fish, and it's because the tip speed ratios are pretty low. Yeah, I think I'm done. That's it from my side. So this is my contact information and phone number. If in case you can contact me offline and open for questions. I don't know how I want to handle the questions here. Who goes first? Thank you very much. So I'm done. Yeah.
Thank you very much. Very interesting design, and then actually the application, as you say, is huge. The challenge of replacing diesel generators from telecom towers, we know since a while that is a huge potential for small wind or for hybrid technology, but nobody has really solved the issue. No, so I wish you all the best, and also that it goes further. I will start. I don't see here Soren Jensen from Solid Wind Power in the room. So that means I will go ahead with the questions I have, and I will start from the end, from you directly. So I wanted to ask you, the first question is about cost, because it seems like you can reduce a lot of the cost of a normal, typical wind turbine. So do you have any reference of how much cheaper can be to have your turbines compared to a similar in terms of
that's a pretty good question, actually. I mean, if you see the standard wind turbines, the cost is ranging from $4,000 to $8,000 per kilowatt is the standard price. But that one is without the mast. That's the hook, actually. And depending on the location or the place, this mast can cost you like $5,000, $2,000, or even $10,000, right? So this is, everyone ignores that. They only focus on the cost of the wind turbine, but the mast is significant. Sometimes it could be 2 times more than the wind turbine. But we are still within that competitive range of the price. So we are on the lower end of 4 to 8K. So we are competitive, but the biggest advantage we get is we don't need a crane to install it, and we don't need extra mast. But if you find a mountain tip or whatever it is where the wind speeds are usually high, you can just directly carry it with 1 or 2 people and just directly install it right on the top or tip of the mountain without even having a small need for a small mast. You can take advantage of multiple. There are many locations where you can put it directly and then take advantage of the wind energy there.
Yeah, perfect. And what about safety or protection for the turbine in case of the high wind speeds? Let's say you have a telecom tower in Southeast Asia, and then you have a storm or something. Is there any protection within the turbine that it will protect the turbine from rotating too fast?
Yes. That's it's a very good question. So actually, we have. I mean, I'm not talking about the electric or braking system. So we can flare the angle of the blades so that it stops rotating at all completely. It's possible to do that. So we have to synchronize. We can measure the wind speed because we have a wind speed sensor and wind direction sensor. So based on the speed, if it crosses, it slowly crosses certain speed. It doesn't stop immediately. It slowly starts flaring away. So all you have to do is you have to turn it by 90 degrees. So we can, as soon as it goes beyond a certain RPM, we can slowly start reducing the RPM by flaring the blades. We just have to change the angle of the blade. So in order to stop it, we have to just rotate the blades by 90 degrees. Then it will completely stop rotating. So it's a very simple mechanism. We already built in and we have tested it. It's working great.
Yeah, perfect. No, thank you very much for the information, and all the best, as I mentioned. I wish you can tackle the problem of a telecom tower that is a huge potential.
Yeah, we have many waiting customers. They're pushing us. But the point is the new technology need to develop a lot of things. Because of the COVID, it's lockdown. We couldn't do the field testing. A lot of restrictions here in Germany. But India, I see that it's all open. So I'm planning to. I'm an Indian, so the customers are also in India, so I'm planning to move to India and start production there. So looking forward to that.
Yeah, thank you. And we're happy to support you from the association. So thank you very much. So now I will go back to Suresh, and it's also very interesting, as I say, very interesting research and study, because at the end we know we all be happy to have all kind of renewable energy installed, but at the end we are kind of small wind is competing with solar energy at the end, because from the point of view of the consumer, when you have two options, you have solar, you have wind, small wind, then of course it's more practical to go for solar because you know what you are getting. I mean, it's much easier to get the potential when you install the solar PV than small wind. Small wind you will need to measure or to know what is your wind resource before that. So the way you are doing that, you are basically, let's say, taking a specific area and say, look, there is a huge potential here for small wind. Is very helpful. So, but do you have any plans? I mean, do you have any plans to go to policymakers in one of these regions or districts and say, look, you have here a huge potential, maybe, but you just need to have some kind of incentive, financial incentive, so people go ahead, and then you have probably local manufacturers or you create some jobs. So what are your plans to do with this study? Are you gonna go to policymakers, or what is the next steps?
Correct. So we've like already just started the study of the policy. So I have like some few slides and all with me, but since that was not the topic of the presentation, I did not go through that. So I mean, like the main, the objective while starting out was like, for example, if you go to policymakers and say that like small wind turbines is a technology that can be used, so they'll be like, okay, why is it not used now, and where can it be used? So to find that first macro level data, we can see, okay, these are the districts where this can be a good option. So if you can formulate policies or bring in rules that are favorable for small wind turbines in these particular districts or in these particular places, that can probably kickstart. So that was the whole aim with which this was started. So the policy work is ongoing to answer your question. Yeah.
Yeah, no, definitely.
Like
It's really
what can be done in the
important.
policy and then what is the
Yeah, we have been discussing in the association actually. I mean, one of the challenges for small wind is also how to locate the turbine in the area you are, because we see even in countries that are very mature, like in Germany, for example, where you have been people is used to have wind turbines, small wind turbines, you still see people who install turbines in places that are not favorable for small wind. Just within the area, no, around the house or something, they have a tree in front. So maybe just as a comment or as an advice, if you can continue with this, would be nice, and then go ahead with the location, specific location of the turbine. For example, in agricultural areas, you can have the open space would be better. Just to go a little bit further, so people at the end, the consumer knows even more. Not only they have the potential, but they have the where to place it, and you help a little bit more with that. And also, maybe a question: do you have any local measurement of wind, or are you planning to have, or do you know? But I mean, just to confirm that the places where you have the potential, if they are good or not for small wind.
Yeah, there is available data from a lot of wind masts that have been set up by NIWE. So we need to go through the process of comparing the data and how this maps out to it. But the problem is that is extremely site specific. So we have not gone into such micro level detail. So probably that can be considered as a next step to validate these places and validate the model. Yes, but that is in the pipeline.
Thank you. I will put you in contact with our vice president Jami Hossain from India. I don't know if you are already in touch with him, but he's a kind of the expert in the association.
Not yet, but
well, he's kind of the leading.
Love to be
He's the leading expert from the association in terms of wind resources assessment, all this stuff. So I think it will be good if he has your study, and then he can even push it more with the contacts he has in India. So thank you very much. I will go back. Thank you for your answers. I will go back to Edwin. Edwin, do you have any experience I mean, your patent has been already deployed somewhere. Do you have any information about any test, let's say physical test?
Oh, there's nothing. I'm only trying to make contact with people in the industry. That's all.
Okay. Yeah, I will use your email to put you in contact with some centers in Denmark and in Austria. They probably will happy to do it to deploy and test your turbine. But if you want, of course. But I will then send you a contact, and I will, if anybody has questions, I will remind you to, you can just write it in the chat, and I will use it. So I will go back to Rabindranath to. I mean, it's very important what you say. You can manufacture locally, and
Yes.
that's one of the key benefits of a small wind compared to solar, is that the fact that you can generate local jobs.
Correct.
You should.
Correct.
Yeah.
I mean, as I told you, there is no supply chain for small turbines. You have to be self-content,
And that's
right from blades.
Yeah, that's extremely important. Also, for usually policymakers tend to forget that a small wind can generate jobs, not PV. PV in many countries will be imported, and then there's no local benefit. So that's very interesting. And I have a question. Your turbines are more designed to be used off grid or on grid? I mean, what is the focal point in India?
Both. In India, it's very less on-grid applications, but in Australia, almost 100% it is on-grid.
Yeah, so it's similar to India, to China, I would say. No, most of the machines are off-grid machines.
Okay,
So,
off-grid, yeah.
yeah, and the question, the new design you show, it has been deployed already, or it
Yes,
just?
yes. My own house I'm using. I showed you the picture, and plus we are trying with cement factories like JK Lakshmi Cements, Ultratech Cements, and in Australia it has been installed as normal wind turbines in open wind conditions. Yes.
Oh, perfect. Yeah, yeah. And the other question I have is, what are the main challenges for small wind in India? You as a company and with a lot of experience.
See, I'll tell you. A simple example. Today you see ministry announces policies after rooftop solar, this thing. Not once they mentioned rooftop. At least we fought in Maharashtra with MERC. Finally, they have agreed. Okay, we allow. Otherwise, they made MSCB, that power has made our client to remove the wind turbine, not allowing connected to the grid. Finally, we myself and my client went to MERC, put in a petition. You should allow anything on the rooftop to be connected to the grid. Finally, Maharashtra has agreed, but not other states. Other states are still not allowing connect any other renewable energy source to grid other than solar. And MNRE, we have put this question many times, but it is not even once in their policy they have mentioned as, okay, you can hook up wind also in a rooftop solar program.
Yeah, it's sad because India, I mean, the country exports a lot of technology, and small wind can be one of them. It can be produced.
Especially now, people are realizing Bombay, you have so many skyscrapers, multi-storied buildings. Now, with last 3-4 years, with extended monsoons, low sun, solar energy generation, now they are looking for, augmenting their existing solar with wind. Multi-storied buildings, rooftops.
Yeah, no, it's very sad. I hope, yeah, the work of Suresh can bring maybe some light to the.
Suresh can play a vital role, sensitizing ministry. They always go blah blah with solar. At least they should, wherever possible, in grid solar roof policy, they should just mention one letter. Even small wind on the rooftop could be considered for grid connection.
Yeah. Yeah, well, I hope also we can do something from the association. That's the good thing about these conferences that give us the information that we need to start promoting and trying to change something in the country. So from the association, we will try to do our best to have a market in India, because it's one of the big countries that is missing in terms of small wind. So thank you very much for the information, and I will go back to Evgeny now. Evgeny, are you there?
No, I think he's gone.
Yes, I hear.
is there. Yeah,
Thank
again,
you.
it's also nice to hear that in Mexico you have some research about small wind. I wanted to ask you about the wind conditions in where you have the research center there. You have very good wind conditions there, or?
We stay near Mexico City in one height to 2,000 meters to and we have 5, 6 meters per second the wind, the air velocity. And this is very good condition for to investigation. We we working more about excavate air velocity from greenhouse, from other installation used to potential to air from fan from this SS, no?
Oh,
It's very interesting. It's very interesting in we investigation and simulation. We have any articles about simulation to direction to hire from fan. It's very good. Thank you.
There's a question here in the chat for you, and do you have any number about the cost of the technology you presented to measuring the torque?
No, the small cost, these devices, fan and wind turbine, and gone to 50% more cost the exchange extract, no? Only. Extractor with wind turbine will cost to more 55. Yes.
Okay, perfect. Thank you. Any plans? Any not plans, but do you know about any local any manufacturer of small wind turbines, or maybe you are trying to develop a machine? No.
No.
Okay.
No, we not have any relation with to fabricate. No.
Okay, perfect. No problem. Yeah, thank you very much for the information. There is another question here in the chat, but this time for Edwin. So somebody asked, what is the efficiency? What is the efficiency increase? How much percentage of this is used to rotate the tubes? Edwin, I hope you understand the question.
Well, first of all, I should say a Savonius rotor cannot spin faster than the wind. So this invention can only increase the torque. That's all. Otherwise, I have to refer you to this U.S. Department of Energy grant report. Let's see, and also that where it states that this Magnus force and in equivalent conditions, this roller, since it has such a low coefficient of friction, will produce 10 times the lift of an airfoil by itself. So I don't have any direct information on it, but it's likely to make everything more efficient.
Thank you, Edwin. Yes, so if there is any other question, this is the last chance. Otherwise, I will close the session because we are almost on time now. So before I go, any final thoughts from the speakers? If any of you want to say something else before I close, this is the time. Otherwise, I will thank you all, and I hope India can be one of the top countries in the near future for small wind. I hope you can create a market, and there is a market for small wind, and you can have locally manufactured turbines also. So all the best, and I don't see any other questions, so I will close the session now. And I remind you before that just after this session, there is another session on small wind in this same room. So you can just stay here, and it will take place in half an hour, I think. Yes. So thank you very much, everybody, and thank you much to the presenters, and it was a very nice sessions, and all the best. Bye-bye.
Thank you.
Thank you very much.
Thank you.
Bye.